Thank you very much. So I guess this is the ethics session. We just heard an interesting talk about fairness, and next is privacy. By the way, since I'm interested in this, how many people in this audience have heard the phrase differential privacy before, at least as a buzzword? Okay, good. This is a new thing. So rather than motivating privacy as an ethical concern, which of course you can do, let me take the alternative tack of motivating it as a practical concern. Okay, I'm going to claim that protecting privacy is important for your business. Okay, and let me just claim this by going through a couple of well-known anecdotes in which privacy was not protected. And let me make the distinction between privacy and security. In each of the three examples I'm going to show you, it was not the case that, someone hacked into a server and got data they weren't supposed to get. Okay, in all of these examples, an organization purposefully released some information. They wanted to release it, but it allowed identifying information that they didn't realize to be deduced about individuals. Okay, so the first example is the AOL search log example. So this was way back in 2006. And AOL did a really nice thing. They said, search logs, the records of individual searches by users are an extremely valuable data set that in the machine learning research community is really hard to get your hands on unless you work for one of the big search companies. So they released publicly their search logs. Now they knew, of course, privacy was important, so they redacted the names of their users. They instead replaced them with random numerical codes. But of course, a moment's reflection will tell you that if I have access to a transcript of all of your search logs, I can figure out who you are. And the New York Times did this. They went and interviewed one of the people in this data set who was perturbed to find that it was possible to discover her identity. There was a class action lawsuit that accused AOL of violating the Electronic Communications Privacy Act, and it sought $5,000 in damages per user of AOL search, which must be at least a six-figure sum. Okay? And AOL's director of research was fired as a result. The next example is the Netflix competition. Okay, they released a data set to avoid having to pay software engineers to improve the recommendation system. And it was the same thing. They removed the names of individuals in the data set and replaced them with unique identifiers. This seemed a little bit safer in their case because the data was just, for every user, a record of the movies they had watched and how they had rated them and when they had rated them. Okay, so there was no plain text here. But it turns out, a pair of researchers who were at UT Austin at the time were able to figure out how to re-identify a substantial fraction of the users in this data set, essentially by cleverly cross-referencing it with the IMDb data set. Okay, again, there was a lawsuit seeking, enormous damages. It was settled for some undisclosed sum, and the second Netflix challenge was canceled. Okay, and finally, and this is one of the more interesting ones to me, was a re-identification attack that was done on data that seemed extremely innocuous. Okay, so this was done on genomic data. Okay, so in genome-wide association studies, what's done is a collection of patients are recruited who all have something in common, say they all have some disease. Okay, and their genomes are sequenced, but the statistics produced are just averages. Okay, so there are in your genome certain positions called single nucleotide polymorphisms. These are places where not everyone has the same base pair. Some people might have one, some people might have another. Okay, and there's lots of these. Okay, so you've got your population of maybe 1,000 patients. You sequence their genomes, and in each of these interesting locations, you just report the percentage of your patients that have each version of the polymorphism. Okay. These are just averages, right? They seem pretty innocuous, but there's lots of them because your genome is big. And it turns out that an interesting research paper was able to show that you're actually, from this data, because there's so many of these single nucleotide polymorphisms, you're able to determine with high accuracy whether someone was in this study or not, okay, which determines whether they had the relevant disease or not. Okay, the costs here weren't monetary, they were scientific. So the National Human Genome Research Institute removed these data sets from the public domain after it was determined you could do this, which restricts the progress of research. Okay, so privacy is important. So I want to talk to you about differential privacy. I'm going to guess that most of you a year ago wouldn't have heard about what this was. We've been studying it in the academic world for about 10 years now, but it's gained attention as a buzzword recently as it's been adopted in industry. Most notably, if anyone watched the Worldwide Developers Conference this year, Apple announced that they were sort of incorporating differential privacy, whatever that is, into iOS 10. Okay, so I want to tell you a little bit about what that is. Okay, here's the Google search trends for the phrase differential privacy. You can pick out the Worldwide Developers Conference. Actually, I was a consultant on this project, and unbeknownst to me, they put my name on the following slide, and this is also a good record of my incoming call logs. Okay, so what is differential privacy? The guarantee it gives is formal and mathematical, but it's a little subtle. So let me tell you what it means first. Okay, it does not promise that as a result of a computation on your data, I can learn nothing about you. Okay, it doesn't promise that. Instead, what it promises is that as a result of the computation on a data set that may include your data, I will learn nothing about you that I could not have learned had your data been removed from the data set. Okay, so I might learn things about you, but I don't learn things about you because of the use of your data. I only learn things about you because facts about the world might correlate with your properties. So for example, if I know that you're a smoker and I run a study on medical data sets and subject to differential privacy and learn that smoking is correlated with lung cancer, I might actually increase my belief that you have lung cancer, but that wasn't what differential privacy will call a privacy violation, because I could have learned that even if your record wasn't in the data set. Okay? So it's promising that whatever it is you're worried about is almost no more likely to occur if you allow the computation to use your data compared to if you don't. Okay, so first a picture and then the formal definition. Differential privacy, by the way, this 2006 paper just won the Gödel Prize, so if you run into any of these authors, tell them congratulations. Differential privacy is a property of a randomized algorithm. Okay, so it takes as input a data set, and it does something, it performs some computation, and it induces a distribution over outcomes. What the guarantee promises is that if I compare the behavior of this algorithm on one data set, and then I see how that compares to its behavior when I run it on a data set that has the data of a single individual changed. Think about this as a data set in which your data has been changed. That the distribution over outcomes is almost the same. It's almost unchanged. Okay, so it's almost independent of any individual's data. A bit more formally, if we think of a data set as a subset of elements from some data universe, we say that two data sets are neighbors if they differ in the data of only a single individual. And we say that an algorithm is epsilon differentially private. There's this parameter epsilon. If, for all pairs of neighboring data sets and all outputs of the algorithm X, the probability that the outcome X is realized is almost the same, up to a 1 plus epsilon multiplicative factor, if the algorithm was run on data set D with your data or data set D prime without your data. Okay. So this definition has a couple of nice properties. Okay, in particular, if I've got an algorithm that is epsilon differentially private, then I can apply any function to the output of that algorithm that I want. I can think about the output of the algorithm, and no matter what I do to it, I'm not going to make the result less private. Okay, any post-processing I want to do preserves epsilon differential privacy. In particular, this is useful when thinking about what the guarantee means. Okay, you can think about the post-processing function f as taking as input the result of your computation, but also everything else relevant about the world, whether a butterfly flapped its wings in Australia, what you ate for breakfast this morning, anything you like. And determines whether the event you care about is going to happen or not. Okay, so when we say that an event X is almost no more likely to occur if you are in the data set compared to if you're not, we really mean any event X. It might be the probability that you are re-identified by a team of researchers in UT Austin. It might be the probability that your insurance claim is denied, or it might be the probability that you receive annoying phone calls during dinner. Literally, if you prove that an algorithm is differentially private, it is a formal promise that none of these events are substantially more likely to occur as a result of the use of your data. Okay. Another nice property of differential privacy is that it composes. If I've got a bunch of subroutines that are each epsilon differentially private, and I run all of them, and I combine their outputs in some way, if I had k of them, then I know that this composition is k times epsilon differentially private. Okay. Well, why is this a nice thing? Together with the post-processing guarantee, it means that I can treat differentially private algorithm design the same way I treat regular algorithm design, modularly. Right? If I have a couple of differentially private subroutines, I can glue them together in any way that I like and just keep track of epsilon as a privacy budget, if you will. And I don't have to analyze directly what might ultimately be a really complicated algorithm. Right? I can reuse my subroutines without having to reanalyze the whole algorithm. Okay, so differential privacy provides, assuming I can give you a couple of basic subroutines for accessing data, a modular language to build private algorithms. Okay, so what are some of these simple operations you can do? Let's start with maybe the very simplest. Suppose I want to compute some number about my data set. Okay, so for example, how many software engineers are in the room, or what fraction of people in the room are software engineers? Well, one thing I can do to compute such a number subject to differential privacy is just release the number perturbed with a little bit of noise. Okay? Noise, it happens to be convenient to use what's called the Laplace distribution. Now, an important question is what is the scale of the noise? How much perturbation do I need to answer a question privately? And the answer depends on what's called the sensitivity of the function, which is just how much the numeric value of the function will change if I change the data arbitrarily of one person. Okay, so for example, the question, how many software engineers are in the room, has sensitivity 1. Right? If I change the resume arbitrarily of one person in this room, well, maybe they weren't a software engineer and now they were, or maybe vice versa, but it's not going to change this number by more than 1. Similarly, with a different normalization, if I want to know what fraction of people in the room are software engineers, the sensitivity of this is just 1 over n, where n is the number of people in the room. Okay, so the Laplace mechanism is an extremely simple thing. It's just going to compute the answer you care about on the data set, and it's going to add a little bit of noise from the Laplace distribution with standard deviation proportional to the sensitivity of the query and the privacy parameter you want. Okay. It's not hard to prove that this thing is epsilon differentially private. And you can analyze its error pretty easily. It goes down as the sensitivity of the query goes down and as epsilon goes up. So if I wanted to estimate the fraction of people in this room who are software engineers with 1 differential privacy, I could get an answer that was correct up to roughly 0.2%. Okay. So that's a simple subroutine. Lots of things like computing gradients, if you want to run gradient descent, are sort of just sequences of numeric computations, but not everything is. Okay, some things have categorical ranges, right? Suppose I want to know what is the modal eye color in this room. It's not clear how I can add noise to an eye color, perturb that, right? How can I answer a question like this with differential privacy? Well, it turns out this is pretty easy too. Okay, all I have to do is I have to define a sort of a loss function, a quality function, how happy I will be with a particular answer. This is a numeric valued function. For example, the quality of an answer read on this data set might just be the fraction of people in the room who have red eyes. And I want to find the color that maximizes this quality score. That's the modal color in the room. So you can think about this for a moment, and it turns out a simple thing you can do that satisfies epsilon differential privacy is to use what's called the exponential mechanism, but it's really just a simple probability distribution. I'm going to select elements from the range that I care about, in this case eye color, with probability that is exponentially weighted towards those elements in the range, those eye colors that have high quality score. Okay? The thing here that's relevant again is the sensitivity of the quality score. And it's not hard to prove that this thing is epsilon differentially private and that it's, fairly accurate. Again, if I wanted to run this query on this room, then what I'd be able to do with the exponential mechanism is roughly find a color that was not necessarily the modal color, but I would have the promise that the frequency of this color in the room would be within roughly 0.5% of the modal color. Okay, so I've shown you sort of the two most basic primitives for computing extremely simple things on data. And I've told you simple rules by which you can glue these things together, right? You've got two subroutines that you can run on your data set, compute numeric valued queries, select things from categorical ranges, and you've got a composition theorem that tells you how to glue them together in arbitrary ways. So let's think about a couple of basic things we might want to do. Okay, suppose we've got a machine learning problem. Okay, maybe it's a supervised learning problem. Quite often you can pose this as what's called an empirical risk minimization problem. I've got some loss function that tells me as a function of my parameters and my data points what my loss is, and I want to find the model parameters that minimize this. Okay, in this level of generosity, it covers almost everything from linear regression to deep learning. Okay, so let's start maybe with the very simplest case, which is linear regression. So I just want to find a vector of parameters theta that minimizes mean squared error. Okay, when I average over the n elements in my data set, I want to minimize the squared error that comes from making a linear prediction with these parameters theta. So the first thing you might do, having seen my earlier slides, is, maybe we can use the exponential mechanism, right? The thetas are some categorical range that we can try to select from. So a natural quality score to define is the mean squared error. You can write that down. And what the exponential mechanism tells you to do is to select a theta that has, with a distribution whose probability is decaying exponentially with its mean squared error. Now, it's not clear how you would go about sampling from this distribution. It's got an infinite range, and it doesn't necessarily have any nice structure. But in this extremely simple case, when you write it down and do the math, it turns out that the distribution is very well behaved. In particular, it's equivalent to the following operation. You could compute the theta that actually does minimize mean squared error, and then just perturb that with a Gaussian that has appropriately selected covariance matrix. Okay. So in this case, it's easy, but it really relied on the sort of extremely simple structure of linear regression. What if we're in the general case, right? What if we're trying to train a complicated deep network? Well, how do you do it without privacy? Right, a popular method is just stochastic gradient descent. We'll start our parameters at some initial value, and then repeatedly we'll pick a data point at random. We'll compute the gradient of our loss function at that data point, and then we'll update our parameters opposite the direction of the gradient. And the reason this works, at least when you try to analyze it, is because the expected value of the gradient on a randomly selected data point is equal in expectation to the gradient of my loss function, the thing I actually want to walk away from. So how can we make this private using what we've seen already? Well, there's a simple thing we might try, which is just to add some noise. Okay? Computing gradients turns out to just be equivalent to computing the averages of a bunch of numeric valued queries over your data set. Okay? Now, we know how to answer numeric valued queries. We can add Laplace noise. It has mean zero, so even when we work with these noisy gradients, the convergence analysis of gradient descent still goes through, because in expectation, our gradients, which were already noisy because we were selecting data points at random, continue to have the right expectation. Okay, and you can run this in practice as well. There's a nice paper out of Google sort of doing differentially private deep learning with a nice set of experiments. So, despite the simplicity of this approach, it actually works pretty well. Analyzing its accuracy is a little complicated, but if you're not an academic, you don't have to prove that it's accurate. You just have to run it and see. You do want to prove that it's private because differential privacy is not something that can be empirically verified. You just have, it's a theorem you need to prove. But it's very easy in this case because this is just the repeated composition of many calls of the Laplace mechanism. So privacy follows from the fact that we know that the Laplace mechanism is differentially private. We know that privacy is preserved under post-processing. Okay, we can add the result of one noisy gradient to our parameter vector. That's just post-processing. And privacy guarantee is composed, so we can just add up our privacy parameters over the number of rounds that we run this algorithm. Okay, so the analysis is simple because privacy is compositional. There's a bunch of other stuff you can do too, but I don't have time in 20 minutes. Let me leave you with just one teaser that I really don't have time to go into detail in. But differential privacy turns out to have implications for learning, not just the other way around. Okay, so sort of a really glib summary of our theorem is this. An epsilon differentially private algorithm cannot overfit its training set by more than epsilon. Okay, private algorithms, if they satisfy this guarantee of epsilon differential privacy, can't overfit. There's some details, but we've got a paper in Science that you can read if you're interested. So let me just give you a very quick sort of cartoon of this. Okay, there's a very simple algorithm we have. Here's the Python code that you can use to gain access to a holdout set in a differentially private way. What does this mean? It means that you can feel free to reuse the holdout set over and over again, which is normally a no-no, but in this case you've got formal guarantees that will prevent you from overfitting the holdout. Okay? So here's a really toy experiment, not on real data. This is synthetic. Okay, just designed to illustrate the theory. Say I've got a data set with 20,000 rows and 10,000 dimensions, and each of the class labels are just binary -1 or 1. And I'm going to do something that feels a little bit like forward stage-wise regression. Okay, so I'm going to try to select the best k variables on the training data, by which I mean the variables that are most correlated with the label. Okay? And I'm going to check whether they're really correlated on my holdout set. And I'm going to keep them only if they're correlated both on the training set and on the holdout set. And then I'm going to fit the best linear predictor I can on these k variables. See what happens when we reuse naively a holdout set compared to when we use differentially private access to a holdout set. And let's see what happens in two settings. Okay. In the first setting, there's no signal at all. The features are entirely uncorrelated with the label. Okay, so you actually cannot, there is no good predictor. No predictor has error better than 50%. Okay? Now, when you reuse a standard holdout, and this is what you're seeing on the left, of course, you're going to overfit the training set. But since you're reusing the holdout, what you can see with the green line is you're actually overfitting the holdout set as well. So you're sort of tricking yourself into thinking you found signal when you're not. The red line is sort of the true error, what you'd get on fresh data. On the right, when you use the differentially private method, you continue to overfit the training set. We're not protecting the training set at all. But the holdout set continues to give accurate answers. Okay, the holdout set is correctly tracking the true error. Okay, so you don't fool yourself. Now, of course, I can prevent overfitting by just adding arbitrary amounts of noise to a data set. In the limit, you don't get to see the data at all. So it's important to see whether you can still find signal in the data set when it's there. And that's what this is plotting. In this variant of the experiment, 20 of the features really are mildly correlated with the target. Okay, so if you can find them, there is a good linear predictor. And what you see is when you naively reuse a holdout, again, you overfit the holdout set and you don't find the correct model. It looks like the best model is to use as many features as possible. But using differentially private access to the holdout set, you don't do that. You find the right model size. Okay. So what I want to leave you with is that differential privacy is a rigorous, provable guarantee that has a sort of formal privacy semantics. It's easy to work with because it's modular. It's got composition theorems and robustness to post-processing, and it can protect against overfitting even when privacy isn't a concern. There's 10 years of writing on this, some of which I've contributed to. If you want to read more, there's a textbook that's, well, you could either buy it for $100, but there's a free version available on my website. And there's a growing literature on the connections between privacy and overfitting that if you're interested, you should check out. So thank you.